Alright, hello, welcome back to our programming tutorial series. It's been a little while. And today we're going to talk about something very important in robotics, especially as you try to get into more advanced things, and that is PID control. So the first thing I wanted to answer while making this video is, what is PID, how is it useful, and then I'm going to show you how to implement it in code. So the first thing that you want to know is, okay, what is PID used for? So PID is really good for maintaining a desired either distance, position, or anything where you have sensor value and you want to maintain that sensor value at a certain point. So a great example of this is like an elevator, right? So let's say you have an elevator on a robot. You saw this a lot in 2018. It'll lift your intake, right? If you want to, you have a sensor on the elevator that'll tell you where exactly the intake is along the elevator, and you want to keep it at let's say 5 feet up, right? So the sensor says 5 feet. How are you going to do this? It's not like the motor will just auto hold there. Well, you're going to need to oscillate at that position. You want to put just the right amount of motor power to hold it at that position. So how are we going to do that? And so this kind of introduces the idea of PID, or PID control, and that's exactly what it's going to do. So let's say you graph, kind of like this graph, what your sensor value are in the y-axis. So this is what your sensor is telling you the motor is outputting, or wherever the elevator is, for example. And this is your time. So this blue line represents where you want to be. So right here is our endpoint. Let's say this is 5 feet. You want it to be at 5 feet. And red represents, where is the motor actually going. So right now this is demonstrating just proportional control. Now proportional control is this. It's this idea of, okay, how far away are you from your desired point? Let's say you're at 0 feet, but the desired point is 5 feet. So it will apply a force proportional to the error. So in this case, my P term is 10, so it'll be 10 times the error. So here at Z, it will go up 10 times as fast until it overshoots. When it overshoots, the algorithm will, notice that, hey, I'm 5 feet above now, so my error is negative. So now that negative error is multiplied by your proportional term, and you'll go back down, and you'll oscillate along the point that you want to be. That's proportional control. That's not good enough, because as you can see, it's good enough in some scenarios if you're able to tune it properly. If you mess with this, you can eventually get to a point where you might like it, but it's not gonna be ideal because it's too much of oscillation. So something you can do is the derivative term. So that's the term you'd like to tune next, and the derivative term is dampening. So it will. So if any of you have taken calculus or just know about it, just by hearing around, a derivative is your instantaneous rate of change. It's the rate of change of a function at any point along it. So if you know your derivative, you can apply a force based on your change in error. So not just your error. Proportional is just based off of whatever your error is. Your change in error can fix it. So for example, if we're approaching 0, if the error is approaching 0 fast, what's the slope of that error? And let's apply a force proportional to that. So what that means, if you kind of boil that down, that means it's a dampening force. So if you increase this, it will dampen it out. Sorry, that was a little too much. But it will slow your oscillations. So see, it'll go and it'll slow down and it'll start approaching a value that you want. If you keep increasing this, it will slow down more and more and more. And something that's kind of really important to keep in mind is these three terms vary very greatly between systems. You're going to need to tune them separately for every mechanical system that you have. So you kind of have to guess around. There's methods for doing PID, the most common of which is tuning P, then D, then I. And you can actually make these graphs, which we'll talk about in Smart Dashboard. But it's a lot of guesswork to try to make these work out. So the more you damp it, it's not doing as much of an effect now. So the other thing that you can do is the integral term, and this one's kind of the hardest to use. Essentially, it adds all your error since your first time, and it kind of accelerates getting to your set point. That way, you can get there faster. It also eliminates what's called steady state error. So basically, let's say you're on the elevator, you know, frictional forces can counteract your proportional term. As you get closer, friction can start counteracting it. So you need something to eliminate that. So it builds up your power, or you know, like your error over time in order to counteract frictional forces. So generally, you want this term to be smaller than P and D. For this system, I noticed if you tune it up to 20, that's pretty good, and then you can put this up to 2. And it'll get there. And you know, that's a really good curve. If blue is where you want to be and red is what you're actually at, that's a good system, and it's reliable. You can spend a lot of time tuning PID systems, and it's actually great for things like turning, which we'll get to. So you have you know, your measurement, your y-axis is what's the rotation of the robot. And let's say you want to get to a 90-degree rotation. It'll, you know, spin to where it's supposed to be and oscillate until you're really facing where you have to go. And yeah, it's super helpful. So that turning example is a great way to segue into our code. So this is where we left our code off. It was, you know, with inserting the Talon SRXs and getting those ready to go. So in this tutorial, we're going to be implementing WPILIB PID. So this can be done with either a spark motor or a Talon. It can be used with anyone because it's running on WPILIB. So all this code is going to be happening on the RoboRio, which is going to be really helpful for us. But there's also another type of PID which runs on the Talon SRX, which we'll get into in a different tutorial. So the first thing you need to do in order to activate PID is to create a PID controller in your code. So that's going to be a public, you really want to be a final PID controller. And this is the object that will be doing all the PID calculations. Because if you saw that spreadsheet earlier, there's a lot of like Excel math going on in here to get this to work. And it's if you want to look up on it, there's great Wikipedia articles that explain exactly how all the math happens. But we don't really want to worry about that. So we're going to just worry about the PID controller, let the PID controller do it for us. So this turn controller needs a couple things to work. It needs a PID output, so it needs something to output onto, so a motor. And it also needs an input, something to read from. So let's start with solving the input problem. The input problem, we're going to need an output. So for our example, we're going to be trying to make the robot turn. And in order to do that, we're going to need to drive our drive base, which is exactly where we are. And, you know, unlike most things, the amount that you're turning is going to have to be one motor going forward and one motor going backwards. It's specialized behavior. So your PID output can't just be a motor, it has to be a function. You're passing your output to a function. So if you've been studying Java, you'll know what interfaces are, and we're going to have to let this implement, oh, I cannot spell, implements PID output. So this whole drive base is going to become an output, and what that'll let us do, if you hover over drive base, it'll show you there's unimplemented methods from the interface. And now we have this, which is our output function. So what our PID output, the output of this PID controller based on the sensor, will be pushed here to this output variable. And then we can do what we want with it. So what we're planning on doing is we're going to set the output. So what we're going to do is we're going to do, you know, left motor, sorry. we're just going to use the set function. It's been a while. Sorry, guys. We're going to do set, and then we're going to do control mode %output. That's what we want to do. And we're going to do negative output, which is the thing coming from the PID controller, and normal output. And this will put our robot into a spin based on those PID values. So there you go. If you look back to our spreadsheet, this red line is what you're inputting into that function. And so now the more intense your PID output wants to output, it will come right into here and drive it one motor backwards, one motor forwards. So there's a few other things we're going to need to do. We're going to need a sensor to, you know, get data from. In this case, we're going to be using a NavX gyroscope and accelerometer. And so you're going to want to install those libraries if you have them. You can also use anything that implements PID input. So HRS is what the NavX libraries call the sensor. So as you can see, let's see if I can actually view the source. I'm not sure if I can, but yeah, I'm not sure if I can. But basically, this will implement PID output. So let's initialize this HRS, this gyroscope. So we'll say HRS equals new HRS, much like most of our objects. And we're going to need to give it a port. So the port that most NavXs are plugged on is that like big, like it almost looks like a parallel port looking thing on the front of the Rio where you slap it on. So that's going to be SPI.port.KMXP. So that's the port that it's connected to. So okay, now we've got sensor data. Now we're going to need to set up that turn controller to do everything and take all these inputs. So we're going to say turn controller, as you might expect. Turn controller equals new PID controller. And we're going to need to give it that P, I, and D constants. These can be changed later on. I'd recommend, making some variables so you can store these. That'll be set up each time. But you can actually change the PI and D at runtime, so that way you can tune the robot while it's working, which is really helpful. For now, I'm just going to set these all to 0, and you can just make PI and D. There's also a term called F. For now, we're not going to worry about F. That's called feed forward. You're welcome to read up more about it if you want, but for now, we're just going to leave all these 0, and we're going to pass these in. This is the opposite formatting of how I used it, so that's going to be annoying. And we're going to pass in KI, KP, KD, and oh, this doesn't even take into KF right now. And okay, yeah, so we're going to need a PID source, so that's our sensor. And thankfully, HRS already implements PID source, so we can just do that. And boom, now you're giving it. Your output is going to be this, the drive base, so you can just type in this. So there you go. Now your PID controller is set up. And let me close this out so it doesn't bother us anymore. So yeah, so you have your turn controller, you have your output, and you have your sensor for input. Okay, well there's a couple things that you also need to tell it. What's the range of input? Right now it doesn't know what its like maximum and minimum input values are. So we're going to have to tell it what that is. So input controller dot set input range. And you want a minimum and a maximum. For degrees, it makes sense that we're going to do 180 degrees and 180 degrees. So negative and positive 180. That seems like a reasonable input from the gyroscope. You also want to set the output range. So, how much are we going to actually pump to that function? For turning, you probably don't want it to go too fast. So I'm going to do like 45% power is a reasonable power to give it. And again, minimum and maximum. And you also want a tolerance. So when do you what's the acceptable amount of error? When do you not want to keep oscillating? When is it time to say good enough, right? So for that, we're going to set the absolute tolerance. So you do dot set absolute tolerance. And for this, we're going to do something like 2 degrees maybe. Seems good. Again, all these parameters you're going to tune, especially PI and D and that absolute tolerance. There's one last thing. When you're turning, it's a circle, so your input, like your maximum input range and your minimum input range are like continuous, right? If you get to a negative 180 and you have 0 degrees, that is not 360 degrees apart. It's only 1 degree apart. So the PID controller has an option for this. You just say set continuous, and it will treat it. So you can read the tooltip here. It'll tell you kind of what I said. So it's making sure these are treated as ends of the same string instead of your absolute minimums and maximums for your input. So there you go. We have this PID controller, and it is ready to rumble. It's ready to turn our robot. So let's create a way for a command to call this so we can rotate the robot. So let's make a function. Public void rotate degrees. Ooh, let's keep our naming conventions proper. Rotate degrees, and we're just going to get that angle that we want to rotate to as our input. Okay, so generally there's two ways of rotating, right? You can rotate to an absolute value or a relative value. For right now, you can make different functions that do different things, but for this tutorial, I'm going to do it relative. So what you're going to do is you're going to reset your navx when you call this, so that way it's kind of keeping it relative. So when you say turn 90 degrees, you're not turning to 90 degrees from where the robot started, you're turning 90 degrees from where it is. So we're going to reset the navx so it's at, degree 0. The input to the PID will be 0 to start with. We're going to reset our turn controller to make sure that, everything's cleared out of there. We're starting with a fresh PID. I would set the PID again, just in case it's been changed. So we can do set PI and D, and we can do, KP, KI, and KD. Oof, I hit insert there. So, there you go. We got PID. And then one more thing. We want to set what our set point, what that, if we go back to the spreadsheet, which I like a lot, what is this blue line going to be? So we can set that by doing turn controller dot set point, and we're going to make that our angle. And one last thing, we're going to turn this thing on. So turn controller dot enable, and as soon as you do that, the PID is going to start running. It's going to start sending inputs to this PID right. That's going to start driving the motors, and it's going to get going. So there you go. This is pretty much doing exactly what we want. We can implement a command for like an autonomous behavior, for example, that'll implement it. So you know what? Let's go ahead and just do that in this tutorial, just so you have like a full understanding of how this works and how to use it. So let's make a command, and we'll just call it turn to angle, and it's gonna implement a command. And let's just go ahead and grab all of these, not that first one, all of these default functions from tank drive. Let's delete this, clean this up. Ooh, we can format this real quick as well, and get rid of these unused imports. Turn to angle. And we're going to want a double angle. And we're going to make a global variable for what angle this whole thing is turning to. And also, a couple things we want to do is this PID controller isn't telling us when we're done yet, so we're going to need to wait a way to tell the robot this command, especially, okay, we're done. So let's make a public boolean, or like a class-based boolean is finished. A class member is really what I want to say. And a boolean is in error zone, which I'll get to that in a second when I'm making the rest of it. So we're going to do our typical command stuff. We're going to make sure that this knows that we're using the drive base of the robot, and we're going to make sure, ooh, let's format this real quick, by the way. Control Shift, by the way, I feel like I mentioned this in the previous tutorial, but pushing Control Shift F is really good. It formats your code, so if you have like brackets on the wrong line, you can just really quickly fix it up. Looks really nice. So we're going to say we're using this. We're also going to say our big angle is equal to the one that we passed in this function, and yeah, and that's about it. When we're initializing, we're going to call that turn controller. So let me try to explain this. The turn controller is acting on its own loop, so we don't actually need to keep updating the turn controller in execute. We just need to call it once, and it'll do its job. All we need to do is turn it off and turn it on. So we know that it's going to turn on the second we do rotate degrees. So we're going to say rotate degrees into that capital angle. And this is going to start the PID. So there we go. The robot is spinning. It's going to go to the set point based on our parameters. But we need it to stop. So this is my way of stopping it. There might be a better way, but this is how I did it in our season. So I'm going to show you. You can get the error of what remember the error is how far away we are from our set point. So we can get that error just by asking the turn controller. You can see robot.drivebase.turn controller dot get average error, or just get error. And now we know what our error is. And basically, we want to know, okay, are we in an error zone that we're okay with, so that way the turn controller can stop. So also to preface, remember when you might be a little confused, but Amr, we kind of set the tolerance, right? It's going to stop when we're within 2 degrees. Yes, the PID controller will stop, but the robot, this command, will not. So we're going to basically emulate that behavior. So we're going to have another Boolean, are we in the error zone, the acceptable error zone. So we'll do it in error zone. And we're going to set both these to false to start with. And we're going to just ask. We're going to say, this is a ternary statement. We do quite a few of these. Basically, if the absolute value of error is like less than 2 degrees, then we're going to say, then in error zone is going to be true. And this is just a Boolean statement. Sorry, not a ternary statement. That's redundant. So this will return true if it is less than 2, and it will return false if we're not in that error zone. And then we can just write a little if statement. So it says, you know, we don't want to just stop it the second it's underneath 2 degrees, because the robot still has momentum, so it could slide out of there if only on one, you know, clock cycle of the Rio you're there. It doesn't mean you're in a good stopping spot. So we're going to do, we're going to have another variable called count, and count will take care of, you know, how many times we're inside this error zone, how many clock cycles we're there. So we're going to say, if in error zone, you know, your count, keep doing that, count plus plus, upgrade that count. And if you're in the error zone, and your count is greater than or equal to like, let's say 5 clock cycles, right? You're in there for 5 clock cycles. Then you know what? Is finished equals true. Actually, I just thought of something you could do. You could make this equal is finished equals if the count is greater than 5. Ooh, and now we have formatting errors, which is why we do that. So, yeah, this statement will return true. So if is finished will become true if count is greater than or equal to 5, and it will become false if it's not. And then if we're not in that error zone, let's really quickly reset and say, you know what, if we're not there, we want our count to be 0. So to kind of recap what this does, this is saying, hey, if we're in the allowable error zone for 5 RoboRio ticks, that means, you know, we're done. This PID controller is done, we can stop. And then your isFinish is going to return our global variable is finished. So that way when we're there and this is all done, this will run, so execute, so quick refresher, execute runs and then isFinished runs, and they keep going. And so if this returns true, that means the command will stop. So there you go. IsFinished will return this, and if we're inside of the allowable error zone for more than that amount of time, then the robot will stop. And yeah, it's as simple as that. Oh, actually, one more thing before we can call this a day. If this command is ended, either by we're interrupted or this controller stops, we need to tell the turn controller to stop. So we're going to take another inheritor, end, which is just a part of, you know, like it's finished or interrupted. It's overrided from command. And we're going to say if we're ending, robot.drivebase.turncontroller.disable. So just turn that thing off. And there you go. Hopefully now you have a better understanding of what PID is, and then this example of, you know, creating your turn controller, having an input device for the turn controller, and having a PID write function. Obviously, if you're doing an elevator, the subsystem is going to look different. Your PID write function is going to look different. You're going to have an encoder probably instead of an HRS, and your command is also going to look different. But it's just, hopefully this gives you an idea of what to do. And yeah, I hope that helped out. So, yep, thank you for watching, and hopefully this helped you understand PID.